for the tea break, and we request if you can come to the front instead of moving back. I have not got the time to introduce our foreign faculty. Let me say a few words before he actually starts the lecture. Dr. Ravi N. Mahapatra is a professor in the Department of Computer Science and Engineering at Texas A&M University, USA, and he was earlier faculty at IIT Kharagpur, and he is almost there in IIT Kharagpur for 11 years before he moved to US. I think I am right, sir. 11 years. Yeah. So he moved to US, and he was almost like 20 years in US.
29 years.
29 years, right, sir. 29 years in the University of Texas A&M, and he is almost a senior professor at 2010 he is a professor in the department, and from that he is a senior most professor over there. And he is also a visiting professor at IIT Bhubaneswar, and he has done his PhD from IIT Kharagpur, if I am right. Yeah, right. So he has a lot of awards, such as Best Paper Award, Eminent Alumni of VSSUT, Distinguished Alumni Teaching Excellent Award, and Distinguished Visitor IEEE Computer Society, Ford Fellow, IBM Faculty Fellow, Boys Cast Fellow. So these are some of the honors he have received. And apart from that, he is also editorial member of IEEE Transactions on Parallel and Distributed Systems, ACM Transactions on Embedded Computing, EuroSIP Journal of Embedded Systems, and International Journal on Information and Communication Technology. He has various research supports from National Science Foundation, Department of Transport, FAA BAE Systems, Honeywell Aerospace, GE Aviations, Hamilton Suzerstein Corporation, Lockheed Martin, Boeing, IBM, National Instruments, Cypress Semiconductor, Xilinx Corporations. So he has the research support from all those organizations. And these are only a few things which I am aware of it. I think the rest of the things, you can visit his website at University of Texas A&M, and please visit the Department of ECE, and you can see the sir's complete biodata on him. With these few words, I hand over the mic to Professor Mahapatra. Yes.
Thank you, Dr. Sai Prakash, for the kind words. By the way, I'm from Computer Science Department. Yeah. Okay, not ECE. ECE, that was overlapping. Can you hear me? The first lecture of GIAN, Cognitive Internet of Things. Okay. The topic is understanding IoT, in which we plan to provide the introduction, then components like in architectures, both classic and reference architecture, then operating systems that make it a complete unit. Okay. And the agenda is besides giving general background, we'll be looking at quickly IoT and its bold vision. That second bullet is usually 1 hour lecture. Okay, I'll do that in 5 or 10 minutes. Okay, about 45 lectures have been kind of compressed to overall the week, but we'll not lose much. If whatever is missing, but that's fine. We'll try our best to give the basic structures is necessary to someone to empower the understanding of IoT and related topics. Then IoT components, we'll discuss that through both architecture, classic and reference architecture. Why classic, why reference architecture, we'll discuss that. Then we kind of saw that multi-layer architecture for the IoTs. Then we dive into IoT operating systems and concluding remarks. Are you familiar with this picture ever? The standard picture. the standard picture called hype cycle of IoTs. In fact, Gartner, okay, yeah, Gartner is a company, they do prediction of various technology. They forecast things, okay? Now, this particular forecast was in 2020. The next one is due in a couple of months, okay? So we'll have a new one, maybe April to July, sometime over there, okay? So all the hype cycles are kind of similar in nature. What you see in x-axis here, there are stages, the 5 stages of hype cycles. One is called, the first called trigger cycle, trigger stage. Then peak of expectations. Then trough of disillusionment. Then slope of enlightenment, finally plateau. So starting from the trigger, it takes a while in the plateau. Plateau means maturity in technologies have done, okay? So, and each stage has its own features. That's one aspect. The y-axis is called expectations, technology expectations, okay? Then, look at those dots. You know what dots are? Dots are actually the technology. Here, it is a hype cycle of IoT. These dots are related stakeholder technologies in this journey. Okay, the stakeholders. Let's take randomly, because if you take each one of them, that will take for a whole hour, okay? Now, look at anyone, it's not clear here. Think about, let's say, there are kind of red, black, yellow. This has been illustrated here. If there's a yellow triangle, which means more than 10 years, that technology is going to plateau. So the objective is, after being triggered, they take various stages of developments, then they become matured, which we call plateau of productivity. At that point, technology has been matured, and it's kind of a good shape, no doubt. Okay, sometimes I consider this as the storm. Suppose the weather guy predicted that the storm landing at Andhra Pradesh so and so hours, it will last for 12 hours. They forecast it. You expect that. But when it happens, it may be 50 miles away this side, that side. Wind speed may be not 200 kilometers per hour. It could be 150 or 100. So it's like that, it's much more than that. So they expect something based on the storage inputs, but in actuality, things are different. So it's something, take that pinch of salt, that, okay, this is like that. And all those things, all the technologies told here, the legends have been mentioned. Some will take 2 years to 5 years, some 5 to 10 years, that much time to mature, and some could be obsolete. Don't have to go to plateau, okay? Now, so there's so many. I'm not going to each one of them, but you will be looking at it, easy to understand. But note that they are all stakeholders to push the Internet of Things technology as a whole. They're all different. Some is architecture, some is software, some is OS, some is security, and IoT servers. They're all related to IoT journey. Clear? The hype is essentially defined here as exaggerated claims about the capabilities, expectations, future scenarios, okay, which may be not realistic. Could be oversimplified, complex technical challenges, and so on, okay? And when you talk technology, those dots over there, they're nothing but could be actual hardware, common protocol, and so and so. Now, with that, what is current state of IoTs? The current state of IoTs, initially it was hype state, but people know about it. As I told you earlier, the IoT started late 2000. Things were kind of off and on, but then it became hype state for a while. But that hype is kind of storm is subsided. Okay? But IoT technology never stopped to evolve. It's continuously evolving now. And with the more inputs, what happens? A storm comes, then some things propel it further. Same way here, new technology, new ideas propels it. Like AI is propelling further. Okay? When they did that in maybe 2010 or so, cognitive IoT was not in the forecast. With the cognitive things, it's going more and more, taking more time to mature. It may be different hype, separate from cognitive IoT. Okay? Maybe you can see that this time, 25. So with the real hardware and real applications, we are seeing it's getting mature in healthcare, manufacturing, then logistics, and consumer electronics. Okay? Now, what are the technology? There are many technologies, by the way, but these are the forerunners to make IoT to happen, such as sensor technology, which is the 10 sensors, the chip. Some sensors could be less than 5 rupees, and there are multiple varieties that every day they are coming in. The low-cost embedded systems are all around us. You buy them in very low prices. Then low power connectivity. These sensors are also equipped with additional computing power. But at the same time, they have to communicate among them and among others, which means they should not consume a lot of power. So it is desirable that low power connectivity is must for all the stakeholders, particular sensors. Then your mobile devices is now more than capable. Their processors are kind of half a Cray. Cray was a supercomputer a long time back in the 80s. Okay? Their power is half of that Cray. Okay? Then even this is pretty powerful. It's no longer the sigh giving time. You do almost same thing over here. Some call comes, you just listen here and answer that. Authentication comes, you answer that. There's so many things you have been doing that. Okay? Then another element is internet with cloud. Without or with cloud and internet is not all. Internet and cloud. Internet and cloud. Then your platforms. There are so many platforms. Amazon, Google, IBM, Cisco, there are so many platforms are there around that. So the technology behind IoT, all this propel the IoT towards the further success. Sensors, that's okay, let's move on. Some applications of Internet of Things. You can see intelligent traffic. What you see here? There are traffic lights are here, okay? You know what is new one now? New one is intelligent traffic without traffic lights. Without traffic lights. The vehicle will have the sensing that where they are, who are the other vehicles around it, okay? Who are the vehicles around it. Then it make the speed adjustment, cross the crossings, okay? Make the crossings move. So that is actually possible with the more intelligent into that, using more analysis, more deep learning activities, okay? Then here you see smart wind farm. Like that also smart solar farms. We in fact, actually last semester some of my undergrad students, they built a unit, a smart solar, what do you call that, charger, then prediction, at the same time the cost analysis is for the consumers actually, which will be used and connect to various corporates. That's a good business actually. So this is like wind farm, but wind can be only somewhere, but wherever there is sun, you can have the solar farms. Okay? Then you have got precision agriculture, a lot of demand, disaster relief. Okay? And besides that, you have healthcare, transportation, food, technology. This is much newer. There is something called Internet of Meat. It's part of food. Okay? It checks the production of beef, okay, how they are being products and how much time they are staying in the industry, how much the transportation, how they are sold. They have a tag, it keeps track of everything, data is collected, analyzed, and improve the loss to be reduced and profit to be more. Then disaster predictions and smart homes and so on. That's so many, that's sky's limit. That's called IoT for everything, okay? So what is IoT? Let's have a formal definition. We talk about IoT, but we have not discussed about the formal definition. This is one of the most recent definition. The IoT can be, sorry, I'm more further, okay. The IoT can be viewed as a global infrastructure for IT, enabling advanced services by interconnecting both physical and virtual things based on existing and evolving interoperable. What is this word? This is a very powerful word, interoperable, for IoT season. We'll be talking about more often in the afternoon, okay? Interoperable. Information and communication technology, okay? People call the ICT actually, okay? So this is the IoT definition. So what to take away is, well, we are thinking IoT as a global infrastructure. It's not something in this room or this university, I mean, this institute. It is everywhere. You can have some kind of IoT infrastructure which can expand from India to Africa and another country too, or globally, okay? Then, this is an interesting slide actually. One to many to any, okay? So this slide provides information from 1960 to 2050, almost century. So what is going on here? Okay, in the x-axis, y-axis, volume, users. Okay, users. Then the different curves. Legends are here. I'll talk about that. Then you see some rise or some informations putting here and there, such as Internet was born 1970, though it was active 1990 in a big way, but it started 1970. www 1991, social media is active 2000, mobile, broadband, smartphone, tablets, almost same time. Okay, then connected cars, it's kind of 2016, 17 maybe. Then Internet of Things, 2020 late. It's kind of going big way. Those started from here, but it's kind of visible more here. The mass wearables are pretty much there. Okay, then if you look at future, cognitive computing is showing here, 15 years before, but I doubt this will be essentially, this will be going towards left, the way things are going. Same thing, artificial intelligence over here, but it is but these are different meaning I'll explain. And what you see here, there are 4 legends here. One is mainframe, means one computer, many people. Servers, big servers actually, many, one person. It's not one computer, many people. So look at where it's lying. It's lying pretty much x-axis, horizon. That means it's not going to go away. It was there, 100 years is still there, going to be there until this year. Then let's take over this next one. Which one is next one? PC, one person, one computer. Okay, 60, selective, only few PCs were there, right? Few PCs there. Then, sorry, here, 1970s. I remember that. Okay, it's going all the way here, in a surge here, then going down here. Why it is showing a peak and going back here? Any idea? This explains clearly here. Now, in the beginning, resources were less, applications were less, so people are using these things. And more people are started using when they can afford and move on with more technology coming, computer become cheaper. Then at that point, mobile broadband, smartphones came up, okay? And social media also showing up much before that. Then when you have mobile, many activities people can do on their mobile. They don't have to depend on PC. So the PC now declining, because who's taking the space? The space, who's taking the space? Laptops, sorry, iPads, your other pads, okay, Androids, and mostly actually mobile. iPad got lost in between, okay? Its mobile is basically taking care of, so many people, the limited use, checking email, communicating, message, all that, they don't have to use a PC, okay? So like that you can explain everything over here, okay? That's some called this interesting graph. Now, look at this red one. It's called Internet of Everything. So that it keeps up, picking up. No way to come down because it's going to be further off. After this cognitive IoT, Internet of Things coming, it is going to shoot like a rocket, okay? And rest of them is possibly you can guess it. But let's not spend too much time on one slide, okay? Unless you have question, okay? But I think once you know this trend, you can always justify that. Bold vision. Why bold vision? Because things are going beyond even what we expected. It is moving forward, okay? Now, it's expected that in next 5 years, it's making this report. They are good in making reports, by the way. That $12.6 trillion business impact, okay? Automotive IoTs. This year, you will find 400 million connected vehicles on the road. The global connected vehicle market size is expected to grow and worth $446 billion by 2033, 7-8 years from now. It may be more actually, because anything we predict in this area is kind of oversubscribing, okay? Now it was 75 billion 2 years back, now 8 years from then, in 10 years, massive jump, okay? Smart lights, globally 18 billion last year, in next 3 years it will be 38 billion. I listed only few to get a feel of this boldness, what is possibilities. IoT for agriculture, food, meat, they all grow like this thing, but agriculture expected to grow from 15.2 billion in 2024 to 22 billion in 2028. And list is actually more. So you just imagine anything, you create your own vision. Your vision could be extreme, far-reaching. Only you should be the one who can make a great vision where this area, that area, and that's all. Even sometimes seasoned players kind of get confused about looking at the growth. So in summary, IoT is coming in a big way. I would say among all that four revolutions we talked this morning, it's computing, communication, then AI, and what else? The other two is internet, okay? Then IoT, AI. So you find that IoT is going to be massive. Is one of the extreme end revolution we have started. Okay, it's only a matter of time that you guys will be seeing wonderful things in your life. Well, how did you reach there or here? Okay, how did it happen? Does it happen all of a sudden? Something fall down? No. It happened for a reason, and because of few actions, few revolutions happened in the past. But main thing is the availability of variety of embedded devices. A tiny 4-bit, 8-bit to 64-bit embedded processors. Your phone could be 64-bit. Many controllers are 4-bit. Okay? And these devices are coming almost every day in new ones. Okay? Then Next is actually IPSO. IPSO means IP for Smart Object Communication. So in 2008, okay, IPSO Alliance launched. Okay, that means the smart object communication has been implemented, announced, so that people can use it. Then also this protocol, low power, this is personal area communication, okay? In 2010, then 2011 actually, it has been this IPv6 version 6. Now, this enable low power to be existing in all the devices when they transmit, and they can also handle some smart activities. When a device is ready, communication is ready, integration of these two technology essentially gives rise to IoT. Not cognitive IoT, but in general IoT. Okay. Then cognitive IoT could not be thought even that point of time. Okay. Now in 2011, the IPv6, for a long time we were using IPv4. IPv4 means only certain amount of devices could be connected together. But IPv6 changed the entire field. Amazing way. Look at how many devices are allowed. It creates so many IP addresses. 340 undecillion IP addresses. A decillion is 10 to the 36. It broke the ground, sitting down to connect hundreds of billion devices. How many people are there on Earth? 8 billion? Okay, 8 billion. So how many, what is the scope of having devices? Each person, 100,000? You can count it. Okay, you can't remember the password for so many, right? Anyway, so we reached here because of cheap, capable embedded devices, excellent smart communication technology, and overall the launching of this large or potentially very large IP addresses. These two together actually make the IoT very smooth field, and which allows to grow wherever it wants. No restriction on communication, no restriction on creating individual IPs, no restriction on embedded systems. What do you need? You are the sole player in the game. The growth of connected device, these and following few graphs will show us how number of devices are increasing. Okay? Then IoT, non-IoTs, and this cumulative rate of increase about 13%, 10%, 13%, and is up to this year. Then you will find the cellular connectivity, IoT, that means the previous one could be both Wi-Fi and cellular connectivity. This is purely cellular connectivity for this 10, 11 year statistics. Okay, and forecast, they are forecasting that from 24, I'm confused again. From 24, you can see that you have CAGR is actually cumulative grade growth. It's the growth rate. It's 15% going this way, next 6 years or so, okay, in billions. And these are some of the market players. There could be many. India is there. Look at that. Okay, not behind. We are doing a good game over there. Then IoT spending, okay, is billions again. So it's also increasing exponentially. All the three trends you see, they're part of bold vision because it's happening and it's forecast to happen now and 25, next 5 years, things like that. I have a data up to 25, but there are more data you'll see it will be coming up every year. So what are we getting into? Yes, we understand technology moved, IoT is born, then IoT is propelled by IP creating huge amount of IP addresses, low cost, low power devices, great communication technology, okay? They are great, but what to do now? What is on our plate? Okay? Well, our plate has got, you have to see huge data explosion. Okay? You can imagine, 1 hour ECG has got 1 GB. Web blocks are 5 GB per week. Space shuttle creates database of 150 GB. So this is just tip of iceberg. If you consider everything, I have many slides on those data side. I could not have time to put them because we have limited time. Now, big data explosion is possible. These are some of the experience that we have. Then other thing is the challenge, the security and privacy. High stakes. We are going to face serious consequences if we cannot protect our devices. We cannot monitor them closely. And because IoT also opened up another thing, it can connect your network anywhere. If it's not protected, it brings a hole, big hole, and attacks can come through IoT to server and other places. Okay? So secure privacy, we have separate lecture for that. Then platform and standards, the other thing. We'll have actually 1 hour lecture in the afternoon on platform, all those things. But the summary is saying that, okay, there is no standard for platforms. So which means IoT structure, architecture is at loose. It's evolving. It is likely to happen that way to start with. It happened to the human society. People start biting, beating, killing, then people become cool down, sane, set a rule, put law, other situations, police, all that to streamline it. Same thing here, IoTs are kind of growing like mushrooms here and there. There are no constraints, only challenge and challenge, but time will come by following some rules or policies that will also tame. In addition to that, we have issue about bandwidth, where you store so much of data, what kind of bandwidth is possible to use, and power challenges. You will see that amount of power IoT consume could be, many countries are not consuming that much of power. Okay? Top 5 security threats. That's insufficient authentication authorizations. Okay? Authentication means if I want to access a node, the node has to authenticate me that I am the good source, I am not a bad guy. Unless authenticate, I cannot do. Authorize means once I access, I have my choice how much I can authorize you to use or not use. You have been using this authorization anyway. If you connect to your group computer system or server, then some of you, the admin has authorized itself to control who can write files, who can remove files. Then some students can't use, they cannot remove files, cannot add files, possibly in certain ways. So those policies are essentially talking about this. Then lack of, okay, again, insecure network services. The network is a vital part of IoT. IoT is nowhere without proper network services. But are they secure? So this is a challenge. Lack of transport encryption. Encryption is necessary for security. But while you put data, pass data from A to B, we call transporting data, there are no encryption has been made. That's doing slowly in limited area, but that's another big hole there. Insecure interfaces. You connect it to web, cloud, mobile, again, not secure. Then privacy is a question. Read this. Agency intimidation is happening a lot now with the fake videos AI created, okay, here and there. It's possible that some central agency with a political vendetta, they can come and attack somebody. At least they can catch you, put you in the jail for several months. It's happening big time. Okay? That's called agency intimidation. Is also part of that because of lack of security and privacy. It has legal consequences and right to privacy. All things are part of this security threats. let's dive into IoT architecture. We have two kinds of architectures. One is called classic architecture and the reference architecture. What is classic architecture? Classic architecture is about having three pillars. We call that perception pillar, network pillar, and application pillar. Any IoT you want to build, you have all these three things intact, put properly. Then the three-leg desk can stand well. What is perception pillar? Perception area is about physical things. They call it cyber physical things. It's physical part, which has got sensors and devices. They monitor a few things around them in the environment and put that there. Just like there are eyes and ears of human body, perception layer, perception leg. Then you have got networking. How these guys they talk to each other and talk to cloud, or they can talk to application, okay, using communication technologies such as Wi-Fi, Bluetooth, GSM, 5G, 6G, long range communication, and so on. Then the third pillar is application. Immense applications are there. Their users basically make APIs, and through that they can basically talk vice versa. And for that there are platforms available. Okay, so people use platform, build applications, use network, and interact with physical devices wherever they could be, millions of miles away. Perceptions. Okay. This morning I came to know that there's a freezing in my area back in Houston, Texas. So I went to and checked the sprinkler system that we have for the state of that. Usually, because winter, I set it for 1 day per week. If it's on, if it's somewhere it's kind of freezing, what will happen? It will burst my pipe. So I had to go and switch off. I switch off from my guest house here. Okay, I don't have to go there. So this is already there. There are so many things there. Even the lights, you can switch on lights on and off. They're about 30, 40 lights possibly controlled by this Wi-Fi over there, out of 100 lights in the house. Then I can group them so that I can control them, okay, timely. I don't have to go every day outside and say, give the outside lights. Certain times, sunrise, sun will be off, and sunset will be on. But still sometime you want it, bad weather, things like that, okay? So these are all possible there, that's fine, but that is not what we're talking today. We're talking, many things have been already there, okay? We are talking about the next level of architecture, next level of IoT applications. Okay, this is a list of various forms of IoTs, okay? You probably know many things. Now, what you look here is interesting that you have varieties of things. Smart homes, sensor network, wearables, there are internet connected wearables for the healthcare, smart meters. If you look and examine the requirement of architecture, for example, here is not same as here and not same as here. If you look at internet connected cars, they have more, the architecture demands more computing power versus smart meters, right? So what it says here that a single architecture, if you plan, if you think, is not going to meet all of them. So there should be flexibility in the computing power, computer architecture over there, okay? Now that is something, IoT is a different beast. You have to allow diverse types of computing entities to take care of the jobs or tasks over there. Okay? So no single architecture will suit the areas of requirements. Then what should it do? So we should have think and make able to provide what it needs. Now, when you look at the IoT, there are two aspects of communication. Okay? The one is it's always two-way IoT messaging. Okay? Two-way IoT messaging. In this case, the device For example, this device is a smart thermostat at your home. You control from anywhere in the world. This is the U, maybe at home, maybe away. This is a cloud. And continuously, your thermostat is putting its data into cloud. Then from cloud, the user can read this whenever he wants. Then it can change the settings, go to cloud and fix it. That's the way it works, okay? So, but in summary, the devices can talk to user, or user can control device using cloud. The second type is as a gateway, we call IoT gateway, coming in between device and cloud. So the same thing, if I put actually in between a gateway, then everything goes to gateway, and gateway talks to cloud. That's talking about two aspects of IoT communication. Now, as for device gateway and connectivity, you'll see that, just like I told actually, you have Bluetooth, low energy, and near field communication. There are some of the technology already available which can essentially talk to gateway directly. Okay? Sometimes even gateway can be connected directly to Ethernet. Like, if you have this Raspberry Pi, which is with sensors around it, you can talk direct to Ethernet. Okay? Now, back to architecture called reference architecture. And due to wide variety, wide domain of Internet objects, there is no single agreement on IoT architecture. Okay? So a system designer perspective, who will be designing software and manipulate hardware, it needs actually a pattern, okay, of design which can be scalable and it can replicate the solutions. That way, the global architecture view of IoT definition is met. Okay? So how do we start? And also, we need reference architecture so that we can relate. Otherwise, you come tomorrow, come with a new architecture proposal. C comes with another proposal. How do we compare? There should be a reference architecture. You can say good and bad. Then slowly, alliance could be met and decide on or agree on particular standard. Okay? And this way, having reference architecture actually keep the main architecture more abstract. When it is abstract, you think that it is possible to make changes and adapt it. Abstract is always good sometimes. Many of you have read actually algorithms. Then write that to code, programming, right? So algorithm is actually abstraction of the programming. Okay, so similar things actually. Abstract is better sometimes, and sometimes no good if it's little away from the implementation. We'll talk about that later also. Okay. So having reference architecture, keep the architecture abstract and make it a flexible implementation later. There's a wide range of possible situations to change it. Now, in particular, when you design a reference architecture, what are the requirements? We keep in mind that when you set the eyes on the requirements, we definitely consider diversity, form factor, that is small priorities, low power, they're must. Keeping this as a minimum background, then you can think about all these things. How to make connectivity happen, what the way to manage the devices, that is a part of the infrastructure, then how to collect data, how to analyze, the computational part, storage part, then scalability. It must be scalable because there are minimum things you have to maintain for the global stature. Then security and privacy, the must. Then predictive analysis, which is a part of the activities or task of the IoTs, and overall integration to the applications. So these are the reference things. So keeping this in mind, you will find the architectures and proposed in this area. Okay, there are layered architectures. Let me go directly to the architecture rather than. Okay, your reference architecture looks like this. Okay, all devices are the lowest area, lower level, Okay? Then communication, they use HTTP or MQTT so that these guys can communicate among each other, they all communicate further up. There's a layer called aggregation or bus layer, okay, extended service layers actually, that message board. So what happens here, the data collected from this going upward and is coming here, is filtered here. If they want to talk each other, then from there it will go down or it can go off for analysis. And you have a database server here. Events are processed after being stored and analyzed. Then it is communicated to the top layer, which has web portals, you have dashboards, all that nice, goody visualization technologies here, then API management, all the applications could be talk to each other. Okay? And you may have cloud above this. So this is a reference architecture IoT level, that it has communication, computation, storage, and interfaces over there. Besides this standard layered architecture, you can have device management. You can have identity and access management. They're all built throughout the layers. Now, though this is very abstract, you will find in following slides, you can always make 3 layer, 5 layer, up to 11 layers, depending on the structure. So device layers, I think we just talked all those things. Anyway, let's quickly grab all these things, okay? We have devices, direct or indirect communication with internet, your Arduino, Raspberry Pis, they can talk with Wi-Fi and so on, Zigbees. Then each device also has the unique identifier. That way, you know it's easy for authentication, okay? And that way, when the communication happens, they declare their ID, and you can say it has to authorize or not. Then an identifier, this UID is stored actually inside the device in the EEPROM or a flash memory. That way you can change if necessary. At the same time, you use HTTP. I know HTTP is pretty much a bulk entity. It takes more resources, but for simple things, don't have to use HTTP, but MQTT can help. We have actually areas of I think your hands-on exercise you have on MQTT, okay? And this is what device layer actually going to offer. Then communication layer is you can use HTTP for certain applications for MQTT and constrained applications. This is also a powerful protocol, okay? And communication layer architecture is necessary so that the communication between the devices becomes smooth. Your MQTT is a pretty old technology. It started about 25 years back and still successful being done. And most recent one is actually MQTT 5.0. Okay? Then we call actually the broker. They kind of take message as a broker, then give it to others. Okay? I think there are some hands-on lab work actually, possibly Dr. Sai Prakash is going to ask the participant to use it there. And MQTT happens to be very suitable for IoT. Another one is called actually SCOAF. It's a constrained application protocol. Okay? It is much lower footprints. Smaller is better so that you don't spend energy. And now, the multi-layer view of IoT architecture could be one of these. More than that, it's the basic one, 3-layer. In 3-layer, you can look at a perception layer, and this is your network layer. Third is application layer. Okay? All that we discuss actually is pertinent to that. Then 4-layer has got still, you have got perception layer, but you have actually gateway layer, part of network layer actually is coming. So look, this same thing happening here and here, but it has additional layer to make certain things work better. So when you go 4-layer, when your device is complex requirement, then you go for higher layers. You have skill sensors there, you have gateway, categorical taking care of this or that, or this or combination of this. Then you have processing layer, data processing layer there. Now, all your data processing could be something down here, much less here. And now part of network coming down, and it's going to split it actually, putting more computing and networking separate layers. Then your up layer, application layer is as it is. Then you can see 5 layers too, putting a middleware layer there. Middleware layer basically takes the computing partly, okay, and some decision making takes place there. So whenever you have an IoT environment, a decision has to be made, you go for actually additional layer over there. Okay. This is another very high-end architecture from Cisco. They use 11 layers, okay, and similar things. We don't want me to go there. I can't read that there. Just to be aware that how things are changing. So as long as you get a grasp on the technology, the trend, and you understand the idea behind that, you're good. You can be creating new things tomorrow. So now what are the components of IoT architecture? We have got things, they're nothing but small embedded systems with sensors and actuators. You know the difference with sensor actuators, right? Sensor get data input, actuators with output. Example, a dam which collects the water during rainy season. With the monitors, the water level sensors, it was just sensing it. But sometimes open the gate to let water go, that's actuator. Actuator make the motor run so that it push the gate up so that water can go. That's sensor actuator example. Gateway for data filtering, pre-processing, and moving it to cloud and vice versa. And receive commands from cloud. Who gives command? The user gives command to cloud, and cloud gives through gateway passes. So gateway is essentially a control entity between your cloud and the device and the user. Cloud gateways, similar concept. Then you are streaming data processes. So there are some applications you have to make data streams, image processing, video processing, for example. Okay? For that, simple data processor not work. You need a streaming data processor, the GPU and things like that. Then you have to have a storage, data storage. We call data lake. Then big data warehouse, where you deal with large amount of data, valuable data, you have to store there. Usually in the cloud, server and storage. Then control applications. Then machine learning. You can apply the predictive over there. They're part of same bot. Then applications you can monitor and control things. Then data analytics to this, but exports. All those boards see here, the components of IoT architecture. Okay. So actually ends architecture and introduction to IoT, but what is now left for software operating system? Break here or should continue? Break, right? Okay. Okay. Yeah. You can take afternoon this one. Afternoon this one, then the next stuff. Okay. Thank you. Any questions? I'm sorry.
Thank you, Prof.